Okay. Chapter 10 is about correlation, and I know that you've talked about correlation in both Algebra 1 and Algebra 2. And in fact, in Algebra 2, you took it as far as talking about like linear correlation, quadratic regression, all sorts of cubic regressions, quartic, different types of regressions. We're strictly sticking to linear. So if you see something that looks like it could be another form of regression, that's great, but we're really not going to deal with it right now. Okay, so to start off, a scatter plot is exactly what you're thinking. It's the scatter, or I guess they call them scatter diagrams. It's basically a scatter plot. You're going to graph a pair of points. So you're going to take some subject, maybe speed and distance, pair them together, and plot them. On the x-axis is going to be your horizontal axis. Y is your vertical axis. Your x variable is sometimes called, or it is called, the exploratory variable. The y variable is called the response variable. So if this is speed and distance, or maybe I should go distance and time, how do they relate? Distance is my exploratory, time would be my response variable. One goal of plotting these is to pair them, is to determine whether or not there is a linear relationship, okay, and linear is just a fancy way of saying line, between x and y. Okay, so here we go. I got a scatter plot. Here on the x-axis is my exploratory. It's the years of college. Here on the y-axis is my my response variable, which would be the income. So it's talking about the number of years and the salary that's going to happen, or that you get for, on average, those number of years of college. So 0 years is roughly like $40,000. Okay, so anyways, you take a look at these dots, and they look like they might go up. So eventually, and not quite today, but eventually we'll get into this line of best fit, or fitting a line in those dots. Okay, we're not really going to do that yet. We'll get to that eventually. We're more talking about if it's even like worth our time to do a line of best fit. So one of our goal is to analyze data by finding a mathematical equation, best representation of that idea or that data. Basically equation of a line, y equals mx plus b type of stuff. For the purpose, the best means that the line that comes closest to all those points. So here's a couple of non-linear correlations, and I want to stress linear because that looks like a quadratic parabola, but we're not going to do that. So that's got no linear correlation, neither does graph B. Correlation strength. Correlation is the measurement of linear between the two quantitative variables. If the points lie on exactly a straight line, it would be considered a perfect correlation. And as they get farther away from that line, it goes from perfect correlation to strong correlation to moderate to weak. So you can kind of eyeball that idea as to how well they're correlated. For example, this has got a moderate linear correlation. Now, the only difference between A and B is that this would be a positive moderate, and that's only because the lines from left to right are going up. This would be a negative correlation. Here I've got a positive perfect correlation. All those dots fit in the line. Here I've got a negative perfect correlation. And to actually figure out a good, solid numerical representation of that correlation, we've got what's called the correlation coefficient. Mathematical measurement that determines the correlation is called the sample correlation coefficient. It's denoted by a lowercase r. This is not r is, so many successes in the binomial theorem. This is r is in terms of linear correlation and correlation coefficient. Some characteristics about correlation. R has no units, so it's not R equals inches, R equals seconds, R equals meters per second. It's just R. It can fall between -1 and +1, including those. Positive R values show that there's a positive relationship, and a negative value would show that there's a negative relationship. If R is equal to 0, it indicates that there is no linear correlation whatsoever, so they're all over the place. And if you were to happen to switch the x and the y's around by accident or on purpose, that's not going to change the value of your r whatsoever. Changing the units, so maybe we want to put a bunch of points that were in inches and we change them to meters, it's not going to change the correlation coefficient at all either. Okay, so r equals 0, there we go, looks like it's all over the place. R equals 1, perfect fit line going up. R equals negative line, perfect fit line going down. R is somewhere between 1 but bigger than 0. They're going up in a positive direction, but they're not all on that blue line. All those dots wouldn't be on that blue line. Same thing happens if it's a negative number. It's less than 0 but bigger than 1. Going to go through a lot of those points, but not quite hitting them all. I would say maybe this is moderate to correlation that's positive, moderate correlation that's negative. The development of the formula, the book can go into a little bit of this if you want to really dive into it. But the idea is that you have positive linear correlation when you have both x and y are positive and when both x and y are negative. So when you plot them like this, hey, it looks like I got a line that's going up. If you compare a low with a high and a high with a low, that's how you get some points in the second and fourth quadrant. That's how you get bots going all down like that, so a negative correlation. Little to no correlation is when there's no really consistency to those x and y values at all. Okay, so here's the idea. For both x and y, there is defined as a high to be an observed number above its mean. Then the relationship on the previous page can be represented as follows. So if you knew what the average of all the x's were and all the average of the y's were, you could take each individual x, subtract it from the mean, each individual y and subtract it from the mean, and take the product of that. And if you get a positive x and y, then you're going to have a high value. If you get a positive x and y value, you get a low value. Again, if you get a negative paired with a positive or a low with a high, you get negative number. If you get a high with a low, you get a negative number. This all goes into developing a formula. What you could do to calculate R would be to sum up all the points that are divided, each summation by its statistical standard deviation to make it unit free. Finally, we divide by n minus 1 to take that average. Okay, so here's what you could do. You could find the standard deviation of both x and y. You've got your means, and you can do all this with, one var stats for x and y. N would be the number of points. You would have to take each individual point, subtract y, subtract x, multiply them out, then take the sum, and then go 1 over n minus 1. And that's to get R. Or you could take this formula. Okay, I took this right out of the book. You can obtain a random sample of n, and n is the number of ordered pairs. You've got your x values, you got your y variables. It says that the data pair should have a bivariate normal distribution. Basically, it's saying that the x and y together follow a normal curve, and it helps us out with using z-scores, t-scores, and stuff like that later on. Okay, you can take all of your x, and what I would do, and I'm going to tell you this here in a little bit, but you could find the sum of x, sum of y, sum of x squared, sum of y squared, the sum of xy, and here is your computational formula for R. Okay, be careful. In there is the sum of x squared, and then there is a sum of x, and then parentheses squared. They do not mean the same thing. Okay. If I went too fast on that, you can flip back, look at it again, and it is in the book. But here's the example I want to use. I've got in the desert, there is a linear relationship between the wind velocity x and the drift rate of the sand dunes y. So 70, 115, and so on, 345, and so on. I got my x and y's. I made a scatter plot off this. X is my exploratory axis here. I put my wind speeds. Y is my response variable, and that's my y of my drift rates. And I plotted these, and it looks like they've got a positive linear correlation. I think I could fit a pretty decent line into there. So here's my x lists, y's listed. I could go sum all the x, sum all the y's, sum all the x squareds, sum all the y squareds, and find the sum of all the x, y. Or you could do what I put right there. Put all this stuff into your calculator. Go L1, go L2, do 2 var stats, and you could get all of those numbers. You don't need to list those columns. Write those numbers down, and in fact, I'm going to ask you to write down those numbers, and then you can go through and you can put where those numbers belong. So the sum of x times y goes right there, sum of x, sum of y. I got my n, which was 7. It's 7 because there were 7 ordered pairs that I got it from. Do some math, and you get R is 0.949. So that means that there's a strong positive linear correlation between the wind velocity and the sand dune drift. And there's a strong one because R was close to 1, positive 1. Okay, now where R is the sample correlation, this little letter here, it looks kind of like a P. It's not a P. It's actually the Greek letter rho, and rho being like R. That's the population coefficient. We'll do some testing with R a little bit later on in a couple sections, so just kind of bringing that up right there. Beware that high correlation does not imply cause and effect. So just because I've got a positive 0.949 between the wind velocity and the sand dune, that doesn't mean that wind velocity necessarily causes the sand dunes to occur. Cause and effect are totally different. Causation is totally different from correlation. And there's actually some pretty cool websites that shows you some pretty cool, crazy correlations that exist with numbers that aren't at all causations. Okay, we have a little lurking variable that can affect some of the stuff. So a lurking variable is neither the exploratory variable nor the response variable. Beware, lurking variable may be responsible for the evident change in X and Y. So there might be some sort of other thing that's changing the data that made X and Y have this linear relationship. For example, countries with high levels of education tend to have higher cell phone bills. Okay, well, is it the fact that education gives you high cell phone bills, or is it the fact that the gross profit of those countries, or the GDP of the countries, is the lurking variable, is really driving both of them? The fact that there's more money in the countries gives you higher education and gives you higher cell phone bills. Again, correlation between averages. If the two variables of interest are averages rather than raw data values, the correlation between the averages will tend to be higher. Okay, so there we go. Page 595. Try these problems out. Bring them to class tomorrow. I'm going to show you some pretty neat calculator tricks that are going to help you out with this a lot.